This video has some solutions to the end of problem, our review set of problems from Chapter 10. Numbers right here. 71. The answers in the book for 71 are wrong. So I'll give you the solutions here with the correct answers. And grab my calculator. Hold on. Alright, so we have here a half Atwood's machine with a pulley that does have some mass. So both of the masses are 6.2 kilograms. Both the same. Over pulley, the radius of the pulley is 24 thousandths of a meter, or 2.4 centimeters, or 0.024 meters. And it has rotational inertia given as 7.4 times 10 to the negative fourth kilogram meters squared. Right? String does not slip on the pulley. It's not known whether there's friction between the table and the sliding block. All that means for us is we can't make a force diagram for this block because we don't know if there's friction there or not. We know that there's tension here. I'll call this T2 and I'll call this one T1 here. So here, friction? I don't know. Maybe there is, maybe there isn't. We could figure that out. If there was a part E of this problem, they could ask us how much friction is there, and we could calculate that, but they didn't ask that. Now, we know that when they're released, the pulley turns through 0.65 radians in 0.091 seconds. We do know that. And we know that the acceleration is constant. So that means the angular acceleration is constant, and we know that it starts from rest. So one possible issue you could have if you're looking for angular velocity and you just did this divided by this, that would give you an average angular velocity. But the angular velocity is changing, so we have to use angular kinematics to do this. So that would be the equation. Theta is equal to 1/2 alpha times time squared plus initial velocity times time, but that's 0. That's 0. So plugging our values in here, 0.65 radians, 1/2 alpha times time squared. We should be able to find alpha there. Let's do that. So 0.65, multiply the 2 up there, and then divide by 0.091 squared. That gives me 157 radians per second squared. And right off, that's part A. Find the angular acceleration. And right off the bat in the book they have a wrong answer for that. Not really sure what they did wrong, but they have the wrong answers. The magnitude of either block's acceleration. Well, if you want to know the acceleration, they're both attached to this string, right? So that means the linear acceleration is equal to alpha times r, where r is the radius of the pulley. So basically we're finding the acceleration of the string, and the string's attached to these, so that's the same acceleration as that of the blocks. So that's 157 radians per second times the radius of the pulley, which is 0.024 meters, and that is about 3.77 meters per second squared. Right? And then they want to know the string tension T1 and the string tension T2. So for part C, the tension T1, I know that the block here, the sum of all forces on that block is gravity minus tension. It's going down, so tension is losing, and that's equal to mass times acceleration is equal to mass times g minus t1, and I know the acceleration, so t1 is equal to 6.2 g minus 6.2 times the acceleration, which we just found. So let's calculate that. 6.2 times 9.8 minus 6.2 times 3.77. That's about 37.4 newtons. T2, oops, D. I can't do the diagram for this block. I can't use block 2 to do it. So I have to use the pulley to do it. And I know that the sum of all the torques on the pulley, well, there's the torque from this one, which is winning, right? Pulley's rotating this way. So that'd be T1 times R minus T2 times R. That torque is losing. That's how we're going to do that. And maybe it's just worth saying that the reason that I don't need the sine theta term in here is because a string on a pulley is always going to come off at a 90-degree angle, no matter what we do. If you try to pull off at a different angle, then the point of contact will change and it will still be perpendicular there. So strings and pulleys, always perpendicular. So let's see here, that's I alpha equals T1 R minus T2 R. And let's go ahead and plug in our values. So I know what I is, 7.4 times 10 to the negative 4 times alpha, which is 157. That's equal to T1, which we found here, 37.4, times the radius, 0.024, minus T2, which is what we're looking for, times 0.024. So we can jam all that into our calculator and see what we can do with that. So let's see, I got this. This is going to come over to the other side. So 37.4 times 0.024 minus this. 7.4 is 10 to the negative 4 times 157. And then I'm going to divide that by 0.024. My answer divided by 0.024. And that gives me tension 2 is 32.6 newtons. We would expect those to be fairly close. Right? But this tension was winning. That's how you do that. So that's kind of familiar. I mean, it's a lot like problems that we did with forces back in chapters 5 and 6. All right, that's number 71. Number 77. What do we have here? We have a record turntable rotating at 33 1/3 revolutions per minute, and we might just quickly multiply that. 1 revolution is 2 pi radians, and 1 minute is 60 seconds. We've done this a few times, so multiply by 2 pi, divide by 60. So 33 1/3 times 2 pi divided by 60, and it's about 3.49 radians per second. So there's that. And it's going to slow down and stops in 30 seconds after the motor's turned off. So this would be like the initial velocity, and the final angular velocity would be 0. And that takes 30 seconds. All right. Find its constant angular acceleration in revolutions per minute squared, and how many revolutions does it make in this time. So there's a way to do this problem with, you could leave everything in the units of revolutions in minutes, and you can do it that way. So if we want to find the angular acceleration, knowing these variables, that's going to be the equation. Looks like this. So my final is 0, and if I want angular acceleration in revolutions per minute squared, then I have to use revolutions in minutes as my units everywhere else. So that would mean the time would be half a minute, and my initial would be, I would keep with 33 1/3 revolutions per minute, and then that'll give me the right units. So its acceleration will be negative this divided by 0.5, so it'll just be twice that. My angular acceleration will be negative, it's slowing down, 66 2/3 revolutions per minute. And that makes a lot of sense if you think about what acceleration is. And then B, we want to know how many revolutions does it go through in this time. Well, that's like finding theta, right? So using those variables that we know, starting with the ones that we know here, I would use the equation, equals, oh, I guess this is the one that uses alpha, right? That's okay though. I can do that because I know that now, because I found it in part A. You could have also used the, well, I guess that's you could have used the fourth equation, which we don't use that often, which is that theta is equal to 1/2 times initial plus final velocities times time. We don't use that equation that often. That's basically average velocity times time. But I'll use this one, so I wrote that down first. So final velocity 0, initial velocity 33 1/3 squared plus 2. Since I'm doing this in revolutions per minute, I would need to have the revolutions per minute squared version of that, which I do have, 66 2/3 times theta. So theta will be 33.3 squared divided by 2 times 66 2/3. About 8.3, 8 1/3 radians. Sorry, not radians. We're doing everything in revolutions in minutes, so that would be revolutions. If you wanted radians, just multiply that by 2 pi. That's number 77. You could have done it all in radians per second and then converted back. I think that's a little bit more cumbersome there, but you can do that too. Next, number 81. We have a thin uniform rod, has a length 2 meters and can pivot about a horizontal frictionless pin that's through one end. It's released from rest at an angle of 40 degrees above the horizontal. Use the principle of conservation of energy to determine the angular speed of the rod as it passes through the horizontal position. Alright, so we're starting with the rod like this at 40 degrees. And then we want to know how fast it's going here. So at the start, we're going to have all gravitational potential energy, and then if we take this to be the 0 level, that's going to turn all into the kinetic energy of rotation. So I got to do a little bit of trigonometry here to figure out how high. The center of mass is in the middle, and that's 1 meter since it's 2 meters long. So I've got a triangle here, 1 meter, 40 degrees here, and I need to know that's where the height, the center of mass starts. It's going to end at this level here. So that looks like that's the sine component of this triangle, and since that's 1, it's just the sine of 40. So 0.643. So the change in height of the center of mass is 0.643 meters. or 64.3 centimeters. So I think I can do this now. So that would be mg delta h of the center of mass is equal to 1/2 I omega squared. The mass of the rod, I don't think they told us that, did they? But I don't think we need to know either. We should cancel out. So m times 9.8 times 0.643 is equal to 1/2. The moment of inertia of a rod about its end is 1/3 ml squared. It's 2 meters long. We got this from the parallel axis theorem, but it's one that we just kind of know now. I can solve for angular velocity. The masses cancel out. And is that what they wanted to know? What the angular speed of, yep, they just want us to solve for that. So it's like we're just about there. So on this side I've got 9.8 times 0.643 and multiply by 2. And then I'm going to divide by 4 squared over 3. 2 squared, which is 4. Divide by 4/3. And then take the square root of that. So my angular speed when it goes through horizontal is 3.07 radians per second. And that's number 81. Good. All right. So conservation of energy, not too hard. These problems. That was number 81, so now number 83. We have in figure 1038, let's see where that is. Okay, so that's our Atwood's machine. So I've got this kind of Atwood's machine with a big old pulley that has mass. The masses are 0.6 kilograms and 0.4 kilograms. Are connected by a massless cord that's wrapped around a uniform disk of mass 500 grams. And it has a radius of 12 centimeters. And they say it's a uniform disk, so that means it's a 1/2 mr squared, moment of inertia. This can rotate without friction on a fixed horizontal axis through its center. Cord cannot slip on the disk. The system is released from rest, and we want to find the magnitude of the acceleration of the blocks, tension, and T1. Cord at the left and the right. Okay, I guess I have to pay attention to which is which. T1, the cord on the left. So this is T1, and this is T2. Did I put the masses the right way? Yeah, I think I did. So our answers should match up with theirs if we do that. Okay, so this is the same. We've done this problem before. We're going to have 3 equations. I'll start with mass 1. I'll do mass 2, and then I'll do the equation for the pulley. Okay, sum of all forces on mass 1. Mass 1 is the lighter, so tension's winning. On block 2, gravity's winning. And on the pulley T2 is the winning torque. So the net torque is T2R minus T1R. You cannot forget the R terms in there. Alright, so let's see. I've got the mass of this one, which is 0.4 times A, is equal to T1 minus 0.4 G. Here I have mass times acceleration is equal to mass times the acceleration of gravity minus T2. And here, the sum of all torques is I alpha. So I'm going to do a couple more steps here. I alpha, that's T2R minus T1R. The moment of inertia of a disk, it's like a flat cylinder, is 1/2 m times r squared actually, I'm going to leave that as r squared for now, for reasons that you'll see in a second. And then here, the angular acceleration is equal to the linear acceleration over r. Remember that a equals alpha times r, so that means that alpha is equal to a over r. So I'm going to make that substitution here. We can make that substitution because they told us that the string is not slipping, which means everything, the string and the blocks all have the same acceleration, and the angular acceleration of the pulley, since the string's not slipping, is connected by this relationship. So then T2r minus T1r. So one of the r's cancels here, and the other one cancels here. Right? So that gives me 1/2 times the mass of the pulley times A is equal to T2 minus T1. And now I have a very similar situation to things that we've seen before. I can add all three of these equations together. The T2s will cancel, T1s will cancel. So I end up with 0.4 times plus 0.4a plus 0.6a, that's a whole a, plus 1/4 of an a, 1.25a, equals, all the t's are going to cancel out, so I have 0.6g minus 0.4g, which is 0.2g. And that's all I need to do there. So I just need to do 0.2 divided by 1.25 times 9.8, which is about 1.57 meters per second squared. That's the answer for part A. In part B and C, they want to know the tensions. Is it 1 and 2? Yeah. So tension 1, go back to this equation here. This is just a little substitution. So 0.4 times my acceleration, which I just found, is equal to T1 minus 0.4g. So T1 is equal to 0.4 times 1.57 plus 0.4 times 9.8, which is 4.55 newtons. And then to find part C, let's use this equation. 0.6 times 1.57 is equal to 0.6g minus T2. So T2, move that to this side, would be equal to 0.6g minus 0.6 times 1.57, which is 4.94. And that's good. That's how you do it. Not too bad. Oh, I just wrote down 85. That's not the next one, is it? Sorry. 87 is the next one. All right, 87. We've got a block on a ramp attached to a pulley. And cords wrapped around the pulley. Let's see what they are giving us here. Wheel of radius 0.2 meters is mounted on a frictionless horizontal axle. A massless cord is wrapped around the wheel and attached to a 2-kilogram box. It slides on a frictionless surface that's inclined at 20 degrees with the horizontal. The box accelerates down the surface at 2 meters per second per second. What's the rotational inertia of the wheel? All right, so let's see what we can do here. I'm going to make a force diagram for my block. This would be mg. I would break that up into its components. right? This old game, so this would be mg, this would be cosine 20, and this would be mg sine 20. Can you see down here? Nope, there we go. And the normal force would balance out that component, and there's also tension here. Only one rope, so I'm just going to call it T. Right? So here, writing an equation for the sum of all forces on the block, I have the down the ramp part of gravity, mg sine 20, minus the tension from the cord. Right? That's the sum of the forces acting on the block. Now, filling this out, block has mass 2 kilograms, acceleration is also 2. 2 kilograms times 9.8 times the sine of 20. So I have everything except for T. So T is equal to, if I move that over here, 2 times 9.8 times the sine of 20 minus 4. So that's about 2.7 newtons. Okay, well, that's not what they want. They want to know what the rotational inertia of this is, the pulley. So writing an equation for the pulley, the sum of all torques on the pulley, well, there's only one. It's only the string. And so that would just be T times R. So the moment of inertia of the pulley times its angular acceleration is going to be equal to T times R. And since the rope is not slipping, that means that alpha, I can substitute A over R, which means the moment of inertia multiplying by R dividing by A is equal to T R squared over A. So the tension we just found is 2.7 times the radius is 0.2 squared over the acceleration they told us is 2. So 2.7 times 0.2 squared divided by 2. So the moment of inertia of the pulley is 0.054 kilogram meters squared. Right? So just a different unknown there. Otherwise, very familiar stuff. 93 is next. Let's see, here we've got a kind of similar situation. We've got a block that has a string or cord attached to it wrapped around a pulley, but it's also being pulled by some applied force. Wheel of radius, oh, maybe it's the same pulley, 0.20 meters. Mounted on a frictionless horizontal axis, the rotational inertia of the pulley, oh, it's similar, isn't it, to the one we just found. It's 0.05 kilogram meters squared. Almost the same pulley. Massless cord, a 2 kilogram block. And table's frictionless. If a horizontal force of magnitude of 3 newtons is applied to the block, what is the magnitude of the angular acceleration of the pulley? Alright, so let's see what we can do here. Let's write the equations for the block and for the pulley. The block, the sum of all forces on the block, it has this pulling force, which is winning, minus the tension, and the pulley, sum of all torques on the pulley. The pulley only has one torque on it from the cord, Bt times R. This is the R. Sorry, I should label that. Alright, so let's start filling this stuff in. So here I have the mass of the block is 2 kilograms times acceleration is equal to P, pulling force is 3 minus T. Here the moment of inertia is 0.05 times alpha is equal to T, which I don't know, times R. So you can make the substitution here. Alpha is equal to A over R, right? Because it's not slipping. We know that that's true. So making that substitution, have A over R, which means could do multiply the R up here, so times R squared. And I know what the R is, it's 0.2. Right? So you could then say, I guess maybe I should have divided that over here, but one way or another you're going to find that T is equal to 0.05 and then divided by 0.2 squared times the acceleration. And then I can plug that in here. So 2A is equal to 3 minus, let's see, what's 0.05 divided by 0.2 squared? 0.05 divided by 0.2 squared is 1 1/4. So adding that over here gives me 3.25. A is equal to 3. So A is but 0.92 meters per second squared. But I think they asked for the angular acceleration, didn't they? They did. So the angular acceleration is A over R. So that's 0.92 divided by the radius, which is 0.2. So that's about 4.6 radians per second per second. And last problem, number 95. We have now a rigid body shown with, oh dear, look at this diagram. So is it equilateral? 3 particles connected to SLS rotated around an axis perpendicular to its plane through point P. If M equals, A equals, B equals, how much work is required to take? Okay, so let's see. We got a. It's not equilateral. So I have a mass of 2m here. No, wrong. Mass m there, and then 2m and 2m. The axis perpendicular, so that means like the axis is going into the page, so it's going to rotate like this around this axis right here. And the distances are B is 50 centimeters. That's these distances. And then these I think are 0.3. So I got that right. Yes. And M is 0.4 kilograms, so this is 0.4 and these are 0.8. Right? And so this is a nice little Pythagorean triple here, 0.3, 0.5, so this would be 0.4 by the Pythagorean theorem. Hopefully you recognize it's a 3, 4, 5 triangle. Okay, so I think I need to, this is 3 particles, so the moment of inertia of a system of particles, I just add up the mr squared for each particle. So I've got, for this particle, it's m times r. R is how far away it is from the axis. That's 0.3 squared. Right? And then I've got another particle just like that here, so there's 2 of these. Plus, this one has a mass of 0.4 times the distance from the axis is 0.4 also. Right, so that would give us the rotational inertia of the system of 3 particles. So 2 times 0.8 times 0.3 squared plus 0.4 cubed, 0.208 kilogram meters squared. And they want to know how much work is required to take the body from rest to an angular velocity of 5 radians per second. Right, so work. I know the moment of inertia, I know these, so work, well, we know that work, net work, is equal to the change in something's kinetic energy, right? So how much work is required? This is the change in kinetic energy, which is final minus initial kinetic energy. The initial kinetic energy is 0. So how much work does it take? It just takes 1/2 I omega squared. That's how much work it takes. You'd have to add this much energy into the system. So 1/2 0.208 times 5 squared is 2.6 joules. And that's it. It's really not that bad. I'm going to say again that the more you connect these rotational problems to things that we have already done, and I think the book and the problems that we chose to do from the book, we're really trying to make that connection and see the way that we can just employ techniques, concepts, mathematical models that we're already familiar with. Mathematical models just means equations, right? Equations that we already know to do this kind of stuff. Cool.